Hi, this is Tim DeStasio, and this is Psychrometrics Training for HVAC Technicians, Part 1. This is a multi-part series designed to teach psychrometrics at the level of HVAC technicians and small contractors. This is not going to be training that's going to go way over our heads and teach concepts that we'll never see or run into in the field. It's designed to help us use psychrometrics every day. Now, you may think psychrometrics is something that engineers have to worry about. It's not something that I run into as a technician or as a small contractor, but think about when a customer calls with a comfort problem. It's too hot, too cold, too humid, too dry. Maybe they have condensation issues. Who do they call? Are they calling an engineer or are they calling an HVAC service company? And is that company sending out a technician or an engineer? They're sending out somebody like you and me, a technician, or maybe you're an owner operator. You are the technician. So it's really important for us to understand psychrometrics at a basic level, but it's also possible for us to understand some advanced concepts, which we'll do in future modules. So what are some of the goals that we're going to talk about today? First of all, we're going to teach the fundamentals of psychrometrics. We're going to provide only the information that we need to know as technicians and nothing more. Information that's useful for diagnosing problems that we find in the field, comfort problems that a technician would run into. And in doing so, we're going to have to explain some of the properties of air. And today we're going to explain the properties of dry bulb temperature, specific and relative humidity, and dew point. That's all we're going to talk about in today's module. We'll leave some of the other properties for another time. We'll also simplify the psychrometric chart and make it a little less intimidating, because whenever we see that psychrometric chart with lines going everywhere, it can be intimidating, but we're going to break it down to its basic properties, and we'll be able to make a lot more sense out of that chart. And in doing so, we're going to see how some of the processes that our equipment that we work on do. For example, heating, cooling, and dehumidification. Can we plot the process of point A and point B on the chart once we understand those properties? Well, absolutely we can, and we can learn a lot from doing that. So let's talk about the fundamentals of psychrometrics. For example, what is psychrometrics? It's simply put, it's a study and applied use of the properties of air. We can get into a lot more detail about that as far as technicians. When we study psychrometrics, we're studying air. And in doing so, we're going to have to learn some of those properties. Dry bulb and wet bulb temperature. We'll talk about dry bulb this time. Wet bulb we'll talk about next time. We'll talk about today two types of humidity, specific humidity and relative humidity. And we'll also talk about what dew point is. Dew point is very important when we're troubleshooting condensation issues. Enthalpy is another property of air. That's something a little bit more advanced. So we'll talk about that at a future module, but that has to talk about the heat removed or heat gained in the process of conditioning air. Another advanced property is sensible heat ratio. We'll talk about that as we design and diagnose advanced problems. So the psychrometric chart, this is the part that everybody hates. It's a chart that looks like this curved apparatus here with lines going everywhere. It's very intimidating, but it doesn't have to be. What we need to understand about the chart is the basic outline of it. It represents the boundaries that air that we live and breathe in operate within. So air that we live and breathe in cannot operate outside of those lines. We have to stay in the lines of this coloring book here. So if we know only two properties, then we can plot a point somewhere on this chart, and then we can now solve for the other properties that we don't know based on drawing lines out of that point. That's what we're going to learn to do today. And of course, the chart can be intimidating at first, but we're going to simplify it very quickly. And the way we're going to do that is we're going to build the psychrometric chart from scratch. So thanks to Carrier, they have a psychrometrics module where some of this early information in our training module comes from. This is what the chart looks like in its very basic form. We're going to start with dry bulb temperature. Now, what is dry bulb temperature? Well, it's a temperature that a normal thermometer or thermostat or weather report measures. So if your thermostat reads 75 degrees, then it is reading dry bulb temperature. The limitation with dry bulb temperature, though, is it does not take into account the moisture in the air, and that moisture has heat. But we'll get into the wet bulb temperature, which does account for that later. If you notice at the bottom of our psychrometric chart here, there's what looks like a thermometer, and that's because dry bulb temperature is simply reading what a thermometer reads. Now, when we read dry bulb temperature, the scale goes from left to right on the chart. So in this case, from 30 to 120, maybe 125 on the chart. So it plots across the bottom horizontal lines. And then when we're actually plotting a point, we're going to plot that point somewhere vertically from that scale. So here's an example of it. Here's all of our lines on this chart that plot possible dry bulb temperatures in increments of 5 degrees. Let's do a quick exercise. Let's plot 75 degrees dry bulb on this chart. Where would we plot that line? Well, it's right there, right in the middle. So somewhere along that line, if our air is 75 degrees dry bulb, we're going to be able to plot a point somewhere on that line. But to plot an exact point, we need a second property to intersect with that line. So let's talk about specific humidity next. Now, specific humidity measures the actual amount of water or moisture in the air. I have a can of sparkling water right here. This is a 12-ounce can. The specific humidity of this can, if it's full, is 12 ounces of water. So specific humidity is talking about the actual amount of moisture in the air. The unit for measurement is not ounces of sparkling water. It's grains per pound of dry air, or what we're going to refer to simply as grains. Now, to put it in context, there are 7,000 grains in 1 pound of water. So we're talking about a lot of grains here. Now, the grains of moisture, or the specific humidity, plots across the right vertical axis. So the scale that goes from 0 to 180 on the sort of the right side, that is our specific humidity. And those lines run horizontally from right to left, as you can see here. So let's do a quick exercise. Let's plot 60 grains. Which of those lines plots 60 grains? Right there. Okay, now we're ready to plot a point on the graph because we have two properties that we know the numbers to. So let's bring up our psychrometric chart again. Because we know two properties, we can now plot what we call an operating point on the chart. This is where in the chart the current air that we're living and breathing is operating at. It's the current condition of the air. So let's plot that example. 75-degree dry bulb and 60 grains. Here's our 75-degree line, just as we did before. And here's our 60-degree line. So our operating point is at the intersection of those two lines. It's that simple. So now that we're ready to plot more properties on the graph or on the chart, we need to talk about the property of dew point and saturation. And to talk about that or to understand it, we need to think about a big sponge like what's in our picture here. Air is like that sponge. It holds moisture. It can hold a lot of moisture. Now, what happens when you squeeze a wet sponge? Well, if you squeeze it hard enough, it can no longer hold the amount of moisture that it did before, and that water or that moisture starts to drip out. And that's exactly what happens when we cool air. We reduce the amount of room that it can hold that moisture in, and if we cool it long enough, that water will condense into droplets, just like what we see going on here in the picture of the sponge. And that point in which we squeeze that sponge, or where we cool the water and we start getting water droplets, is called its saturation point, because it cannot hold any more moisture without forming condensation. The saturation temperature in psychrometrics is also called the dew point. It's the temperature at which air, given a certain amount of moisture that it's holding, if it gets cooled past that temperature, some water will start to fall out. That's what's called dew point. So it's a temperature that our air has to be cooled to in order to start forming condensation. So where is dew point plotted on our psychrometric chart? Well, it's on the left. It's that left curve right there. So that's really important to understand that dew point is a curve, because when we start talking about relative humidity, we're going to see how it follows that curve. So let's bring back that operating point. 75-degree dry bulb, 60 grains of moisture. There's where our X is. Now, when we start cooling air, we're taking away dry bulb temperature. So that operating point moves from right to left. It doesn't go up and down because we have not removed any moisture yet. It's just going from right to left, just like you saw that X or that operating point just do. Now, something interesting happens when it hits that curve. It can't continue past or to the left of that curve anymore. No, it has to slide down the curve. That's the only thing that it can do. So when it hits the curve, it has no choice but to slide down the curve, just like we see here in this animation. So let's talk about the dew point of air at 75-degree dry bulb and 60 grains of moisture. Well, we started off back at our beginning point, and that's 53 degrees dew point temperature. So if you notice at the intersection of 75-degree dry bulb and 60 grains of moisture, if we go straight from right to left, when it hits that curve, that's our dew point, 53 degrees dew point. So now we're ready to talk about relative humidity. Now it's important to understand the difference between specific humidity and relative humidity. We talked about this can of sparkling water. The specific humidity, if it's full, is 12 ounces. But what happens if it's only half full? What would be the relative humidity? Well, relative humidity represents the percentage of saturation at any given point. So if our can is half full, we would call that 50% relative humidity. If it's 100% full, we would call that 100% relative humidity. So while specific humidity measures the actual amount or quantity of moisture in the air, relative humidity represents the percentage of the saturation at that given point. And relative humidity on the Psych chart curves follow the dew point curve, as we can see here. They don't follow it parallel. As you can see, when you get around 30, 20, and 10%, the curves are a little bit flatter, but they do follow a curve. So let's plot a point using our operating point that we're already used to. What's the relative humidity at 75 degrees dry bulb and 60 grains? All right, so here's our 75 and here's our 60. So we can see our relative humidity, or our operating point, is somewhere between 40 and 50% right there. It's actually 46% when we run the exact numbers. So it's we have to sometimes draw a little imaginary curve if it doesn't land exactly on one of the curves that we have. But there's also apps that we can use on our mobile devices that gives us that exact number. But we know that the relative humidity, if we're just being very broad, very rudimentary here, it's somewhere between 40 and 50%. It's actually 46. So we would draw an imaginary curve between the 40% and the 50% line. All right, let's talk about specific humidity versus relative humidity. The specific humidity is the actual quantity of moisture in the air. It's measured in grains, and the scale is on the right side of the chart, as we've just shown here. That long box is our scale that we measure specific humidity in grains. Relative humidity is the curves. And we have to start understanding what happens when we cool or we heat air. So as dry bulb temperature goes up, relative humidity goes down. Think about what happens if that X in the middle of our chart moves to the right. It doesn't go up or down, it just moves to the right. Where would it intersect? It would intersect with a lower relative humidity curve. So let's illustrate this. We're going to plot 70-degree dry bulb, 50 grains. What is our relative humidity? Well, we see it is somewhere there between 40 and 50%. It's actually 45%. This is our operating point, the red X on the chart. Now, what happens when we increase our dry bulb temperature to 100. We're going to heat our air to 100. Now, we're not adding any grains of moisture. We're not adding any moisture to the air. We're strictly heating the air to 100 degrees. Here's our new dry bulb line, and our X is going to go from left to right. And now look what happened to our relative humidity. Did it go up or down? It went down. It went down to 17%. So that tells us something. When we heat air, we make the sponge bigger. We give it more room to hold water. It can now hold more water. So if we have the same amount of moisture in the air, the percentage is going to be lower because the sponge just got bigger. That's what happens when we heat air. The opposite happens when we cool air. We make the sponge smaller, and so our relative humidity would go up when we cool air. All right, here's the complete chart. So does it look a little less intimidating? We can start blocking off some of the noise, some of the properties that we don't really use. The complete psychrometric chart has all the lines and curves that we just discussed. They're overlaid on top of each other, but if we can just kind of single them out, we can still understand this chart. And there are more advanced properties that we're going to talk about later, but for now, we're just going to ignore them. Let's now plot out our operating point that we've been talking about so far. 75-degree dry bulb, 60 grains of moisture, specific humidity. Here's our 75-degree line. And here's our 60-degree line. And here's our operating point. So it's the same thing. We just are using a chart with a little bit more noise on it. Let's talk about the heating process. So when we talk about a process, what we're referring to is doing something that changes the properties of the air. A process could be heating, it could be cooling, it could be dehumidifying, it could be humidifying. Anytime we change the properties of an air from point A to point B, that's called a process. So now we can track that process on the psych chart, and we can learn a lot from that. So let's use an example. We need to heat a room from 60-degree dry bulb, 40% relative humidity, to 70 degrees dry bulb temperature. So our starting point A is 60 dry bulb, 40 RH. So here's our 60-degree line, and here's our 40 RH curve. So here's starting point A. Now we need to heat that to 70 degrees dry bulb temperature. So we're going to plot the process line. Here's our new dry bulb temperature there in red, 70-degree dry bulb. And here's our new line. So we went straight across from left to right. The line that connects those 2 points is called our process line. So we're simply going to slide right horizontally from point A to point B. Now notice that our grains of moisture didn't change. We didn't add any moisture here. We didn't move the X up or down vertically. So what happens to our RH, or relative humidity? It actually goes down. So again, heating the air doesn't add any moisture to the air. We're not adding any water when we add heat. Think of it as dry heat. That's why the grains remain the same. So that line that connects point A to point B is called our heating process line. Let's talk about the exact opposite, the cooling process. We move left from the initial operating point because we're removing dry bulb temperature. Again, let's do an exercise. We want to cool air from 80-degree dry bulb, 60% RH, to 55-degree dry bulb. So we're removing quite a bit of heat. What's our new relative humidity? Well, point A is 80-degree dry bulb, 55%. That should probably say 60% RH. Here's our operating point A. Now, what happens when we start cooling that air? Well, we need to cool it below our dew point. So our dew point is way down here. Again, when that X goes from right to left, it's going to slide down that curve to point B. So notice that our grains did drop in this case. We started off higher up in the scale, on the chart, and we ended up lower in the chart. So anytime we go from higher to lower in the chart, we're removing moisture. Now, why did we do that? Well, it's because we dehumidified the air. We cooled the air below its dew point, and that air started condensing water droplets out of it. So the new amount of specific humidity, or the new amount of moisture in the air, is a lot lower. So it caused the moisture to condense and fall out of the air, and this is called the dehumidification process. So again, our grains of moisture dropped. Whenever grains drop, or whenever our process takes us lower in the psych chart, we are doing dehumidification. How much dehumidification did we do? When we talk about a difference in specific humidity, that purple line represents how much moisture, how much grains that we lost in the process. Quite a bit here, it looks like. So the cooling dehumidification process not only moves our operating point to the left, but it also moves it lower in the chart. And that's because a typical cooling process usually comes with some dehumidification. We're cooling the air using a coil that the surface temperature is much below the air's dew point. So you think about the typical air conditioning process. What's the perfect evaporator coil temperature that we typically want? It's 40 degrees. Well, 40 degrees is way lower than the current dew point of the air that we bring in. And so when that air touches that 40-degree coil, it starts removing moisture. The moisture starts falling out of that air because we're cooling it below its dew point. The water is going to condense on the coil surface. It's going to get drained out through the condensate drain line. And that condensation is the moisture falling out of the air. So in this case, we're going to plot the dehumidification process between point A and point B. So we see point A, that's our starting point. Point B is our ending point. We know that we're cooling and dehumidifying because point B is to the left of point A, so we're moving dry bulb temperature. It's also lower in the chart than point A, which means that we're removing grains of moisture, so we're dehumidifying. Now, before we talked about the line sliding all the way to the left, it hits the curve, and then it slides down the curve. In reality, that's not what happens. We made that animation just to teach what happens when we dehumidify air below its dew point. In reality, anytime that we're drawing a process line between 2 points, the old adage is what's the closest distance between 2 points? It's a straight line. So we always draw a straight line between any two processes. We don't follow the curve. We just draw a straight line between A and B. So the cooling process moves the X from right to left, and the dehumidification process moves it down. The combined process is a straight slanted line that moves left and down that connects point A and point B. So once we know two air properties as a review, we can plot a point on the psych chart. That's very important. We have two different lines here, two different points that we are plotting. The first one, we see the intersection of two different properties, and now we can plot a point. The heating process is a straight horizontal line from left to right. So we've plotted a starting point. The heating process is going to take us straight from left to right. Notice what happens to that X. It just moves straight across. Doesn't go up or down because we're not adding or removing moisture. It's just going from left to right. Now, the cooling and dehumidification process is a straight downward slope from right to left. So that represents our cooling and dehumidification. We go to the left because we're removing dry bulb temperature. We go down because we're removing grains of moisture. So in the future, in a future module, we're going to talk about plotting the sensible and the latent cooling process. So this is a little bit more advanced than psychrometrics. We're going to learn about wet bulb temperature and enthalpy, and we'll be able to plot what happens when we remove wet bulb temperature, or when we remove or have a difference of enthalpy. And then we can talk about sensible heat ratio and calculating it, and calculating the volume of airflow based on sensible heat ratio. Some pretty interesting stuff. And once we learn sensible heat ratio, we can solve how much airflow we need. And that brings us to the end of our module. So hopefully this has been a very fundamental, perhaps even a review of what you already know about psychrometrics. Maybe it filled in a few gaps, but the purpose of it was just to establish a baseline so that in future modules, we can get a little bit deeper into it and we're not talking over anybody's head. I appreciate you watching. If you have any questions, put them in the comments below. Thank you and stay safe.